As we saw previously, we will need to know properties on our set when we deal with an optimization problem. So here we will focus on subsets in Rn. Okay, optimization problems are more general. They are more. We can work in more general spaces. But let's focus on Rn and try to find the properties we need to develop our theory. So the first important thing we need when we work in our set to compare the position of points in the set. For that, we need a system of measure that we call distance. So we need first distance. First thing, distance. Okay, so distance, the Euclidean distance we define here is the following. So if you have 2 points in Rn, let's call them capital X, x1. So we have yes, in Rn as in R2, we locate points with coordinates. In Rn more generally, we locate them with coordinates like that. So if you have 2 points, y1 and also yn, then the distance, the Euclidean distance that we denote like that is the quantity square root of. So the difference x1 minus y1 square, etc., plus xn yn minus yn. Yes. So the first coordinate of the first point with the first, etc., as usual. Okay. So this, sorry. So these happen. So this distance, you know it already. You had the occasion, but just we don't see it like that. So let's just in dimension n equal 1 see what this relation gives us. Okay. So it means here if you have the distance between x and y, two real numbers. Okay, those are in Rn. Here with n equal 1, I will work in R. So I have two real numbers. That means if I use this formula, it gives me x minus y square root, okay? Which is absolute value x minus y. So which is the distance we know between two real numbers. It's controlled by the absolute value. Okay, so let's n equal to, what is n equal to? So we need 2 points, let's say x1, x2, and y1, y2. So we will have square root of, so you will have x1 minus y1 square plus x2 minus y2 square. And this quantity also, you already met such quantity before when you were working in plane. Okay, so that's yes, and for n equal 3, similarly we will have a third component here, quantity. Okay, the second step, once we have a distance in Rn, the gradient distance, we want to characterize the location of particular points in a particular set. So we will be interested in points that we call them interior points. Okay, so or open sets, or let's call it, yes, let's call interior point. Interior point. What is an interior point? Okay. It's a point that, so x0, we will say that x0, let's point in more general, okay, a point x0 is interior to S. Okay, to S. S is subset of Rn if and only if we can find R positive, so that a ball, what we call ball, I will explain it, with radius R. So let's erase this part. Let's put the radius here, is included in S. Okay. So what is the ball? A ball centered open ball is the set of all points in Rn that are with distance. So here, like we denoted here absolute value, sometimes often we use the notation of norm of the point x1, x2 to the point y1, y2. Okay, we call it like that. Here also it's norm of the point x minus y. Okay, and operation within vectors x minus y, we know how it is between components. Okay, so this is what it says: x minus x0 is less than r. If you look at it in one dimension for n equal 1, this ball is the set of x minus x0 less than r is equivalent to x is minus x0 is between minus r and r. That is x0, x is between x0 plus r and x0 minus r. You see, so it is an interval. That means I will say that my point is interior, okay, x0 here is an interior. If I can find the distance r, so I can put it inside an open interval. So I can x0 plus r and x0 minus r is part the whole interval, small interval. Okay, that means we want to be interior. We need to have more points close to x0 that will be inside the S, the biggest set S. Okay, we want so the whole interval x0 minus r, x0 plus r included in S. We don't need just one x0 and few points. We need the whole interval. If you want in dimension 2, so the norm is the set will be, if you take them, so x1 x2, or let's say x1 y1, x2 minus x2 y2. So I changed the notation here. So here, or let's say x0 y0 and xy. No, we don't need to put 1 here. So we are looking for, yes, the set of the point xy. Okay, so this is equivalent to, we said, to, so if you remove the square root, we will have x minus x0 square plus y minus y0 square less than r square. But then this is the set of points described here. With the equality equal r square, we have a circle. So let's say here, sorry, so let's erase here. Yes. So suppose we have our x0 here, y0, our point, the center. So its center, you will see, it's a circle, okay, with radius r. Suppose this is my distance r. So on this side, so I will be on the units, the circle with distance r centered at x0, y0. Okay, so if I want to remain the distance of the point to x0 remains less than r, I must be inside here. So I will describe finally this area, okay, the disk of, without reaching the boundary of the circle, okay, the disk. So this is my set. So when I say that x0 y0 is an interior point, and usually we denote x0, okay, x0 y0, interior mean we use the notation as with a small 0 here, or like interior of S. Okay, if and only if I have a whole ball, small ball disk, which is the disk here, included in S. Okay, and it's good also to visualize the situation when we are working in space also. N equal 3, then the disk, our disk xyz minus x0 y0 z0 less than r is equivalent to x minus x0 square plus y minus y0 square plus z minus z0 square less than r square. And here again, when you have equality, you are working in a sphere. You are on a sphere. Okay, so we will have something like that here. Suppose I'm in space, so I will have a point, and yes, what happens here, so I will have something. I'm working in sphere. So to be interior point is R3, Okay, I will need to be sure that I have a whole ball like that included in my set. Okay, this is so the surface here is the sphere. Okay, the sphere, but the interior here, interior of ball, interior of a ball. Okay, so BR center at x0, y0, z0. Okay, so this is what we want. And a set where, so this is the meaning of interior point. With interior point we characterize, imagine you have a set S and you can check this definition for any point of this set. We obtain then an open set, we call it open set. Open set. Okay, an open set is a set S is open if and only if for any x in S, x belongs to the interior of S, or okay, or S0. Okay, so it's you can find each time a small ball. Okay, interior point, set of all interior points is S0. So S is open if and only if S is equal to the set of all interior points. Okay, this is what it means. And then we have closed sets, closed category of closed sets. Okay, closed set. As so we have the characterization as is closed if and only the complementary of S is open. Okay, we have then we characterize boundary points, boundary of S. Okay, S. Okay, the boundary points. Okay, there is a characterization of boundary points. Okay. Okay, so boundary point. Okay, S belongs. Okay, point x0 belongs. We denote it boundary S. Okay, boundary of or is the set D the S. If on and only if for any R. Okay. Okay. So, for any R positive, the ball contains, so the ball centered at x0 with radius R intersect the interior set is non-empty, and it intersects also the complementary of S. Okay, the complementary of S0. Okay, complementary of S. Is non-empty. Okay, so intersection with S is not empty. Not the interior with S, just S, just let's correct here. Okay, so we have the sets. What else now? We have then with the size of the set. We have then bounded set. Bounded, we will say S is bounded if there is an existent M positive, so that the distance of X to the origin is less than M. Okay, for any X in the domain S. And bounded is the opposite. So you have also bounded and unbounded. Unbounded set. Okay, unbounded. So is a set that is not bounded. Is set that is not bounded. Not bounded. Okay, and then yes, so this is about then there is a category now where another property we will need. This property is convexity. So here it is convexity. Convexity is another doesn't use distance. So let's put it like that, or let's continue. Or what about convexity now? Now here we need sometimes to move along a line segment, so we need to define the convexity property. So S is convex if and only if each time you take 2 points of your set, then the line segment, so we can characterize the line segment like that, y belongs to S for any t parameter belonging to 0, 1. Okay, so this is what it says. Okay, you can make an analogy with a line segment in the plane. Okay, so this is what we want. Okay, for example, to just to see how see this property. For example, if you are working in the plane and you have a circle. Okay, what about the circle? Circle S is the set of all points xy such that, for example, x minus 0 square plus y minus 0 square equal r square, distance r here. Okay, you have 0, 0, the origin, and y. So this is my set. My set is this one. It's just this line, curved line. Okay, it's the circle. So this circle is not convex. Is not convex. Okay, is not convex. Why? Because if you can imagine a point. If you can imagine a point here, okay, and another point here, they belong. This is E. This is B. So you have E and B belongs to S, but the line segment, for example here, but the line EB, the line segment EB is not included in S entirely. Okay, just visually you can see it. You can always write things well and prove it. Okay, so you can choose one, the middle point, for example. It doesn't satisfy the equation of my circle, so my point is not an S. Okay, so yes, so we have categories of um, family of sets that are convex. Plane, for example, in plane in space are convex sets. Okay, so all linear combination like that. So this is an example where it doesn't work. There is another example here where it works. When you have your set is described by relations that like that xn, such that linear combination of this quantities en xn less than or equal to a number, okay, then this is convex. Okay, in Rn we can check the definition easily. Okay, and we have properties also. Other example, intersection, finite intersection of convex set is convex. Set is convex. We have this property, and yes, so this we can keep in mind as the basic basic sets we will meet, and of course here we don't focus on the theoretical aspects, writing proofs and checking, but more visual. We use more of the visual aspects, and but we need to pay attention to the details, to their properties. Closed sets, open sets, interior point. This terminology will appear: convexity, bounded, unbounded. All these definition must be clear in your mind. You have a clear understanding of those definitions.